Okay, good morning, everyone. Today I'm going to discuss some important results on Hilbert space. Uh, the first one is, let me write this theorem. So a non-empty closed convex subset C of a Hilbert space H contains a unique vector of the smallest norm. So if C is a non-empty closed and convex subset of a Hilbert space H, then we say that there exists a unique vector in C such that the norm of that is the smallest of all the norms of the elements of C. So that means that that is there exists let's say X naught in C. There exists X naught in C such that norm of X naught is equal to infimum of norm X belonging to C, and X naught is unique. You will see that the convexity E of C and closeness are used also, that this space H is a Hilbert space. This is also used. So this result is not true in general if I replace this H by a Banach space. So if you have a closed convex subset of a Banach space, then it may not contain any vector of smallest norm, or it is possible that there are more than one vectors. So you can easily get example where this uniqueness fails. So if you look at say on R2 itself, if you look at the usual norm, the Euclidean norm, then it becomes a Hilbert space, and when you take anything, it is saying that there exists a unique vector of smallest norm. But suppose you take L1 norm or L infinity norm on R2, then you can easily see that you can have a convex set where this uniqueness fails. So, for example, if you like look in R2 and if you take right, so you see the unit ball, if you look at in different norm, so it looks like this square, and here you will have uniqueness, but uh, okay, let me leave the example right now. So of course this kind of result is true in more general Banach spaces. So if it is something called uniformly convex, then this is true. So but let us prove this for Hilbert space. So so we know what to do. So we need to find a vector such that norm of x naught is infimum of norm of x for x in C. So let us write this infimum as D. So let D is equal to infimum of norm x, x belonging to C. Of course, if yeah, so no, this is D, and since this is infimum, we know that we can find a sequence xn in C such that norm xn converges to D. So therefore, there exists then there exists a sequence xn in C such that norm xn converges to D. So we get a sequence such that norm xn converges to D. If somehow we prove that this xn converges, then we will get that because norm is a continuous function. If no, this xn converges to some vector x naught, then norm of x naught will be equal to D. So we will get a vector. So because we are assuming this C to be closed, if xn converges to x naught, then x naught also belongs to C. So we'll get a vector in C. And we'll use that this is a complete space. So if we can somehow prove that this xn is a Cauchy sequence, then by completeness we know that it will converge. So we will try to show that this xn is a Cauchy sequence. So for that we need the convexity and that completeness. No, so we need the convexity of C and also that H is an inner product space. So let's see how to show that this is a Cauchy sequence. So, so since C is convex, if we look at any 2 points in C, any two vectors in C, then the midpoint is also in C. So in particular, if I take xn and xm, so we have xm plus xn by 2. This belongs to C because xm and xn both are in C. So this is true for every m and n. So because this is in C and we know that D is the infimum of this thing. So therefore, norm of xm plus xn by 2, this has to be bigger than equal to the infimum, which is D. So norm of xm plus xn by 2 is bigger than equal to D. So this implies that norm of xm plus xn is bigger than equal to 2D. Now what we want to prove that this xn is a Cauchy sequence. So for that we need to show that norm of xm minus xn, if I take, then that can be made arbitrarily small for large m and n. So now we want to somehow get xm minus xn from this. So here we will use that we have an inner product space. So we have the parallelogram law. Uh, by the parallelogram law, we have norm of xm minus xn square is equal to 2 times norm xm square plus 2 times norm xn square minus norm of xm plus xn square. Right? Because norm of xm minus xn square plus norm of xm plus xn square is 2 times norm xm square plus norm xn square. Now, what we know is that this xm, xn are both in C. So, norm of xm square okay. So, what we know is that this from above norm of xm plus xn is bigger than equal to 2d. So, minus this will be less than equal to minus 2d. So, this will be less than equal to 2 times norm xm square plus 2 times norm xn square minus 4d square. This is by this. Let's call this 1. Now, what we know is that the norm of xn converges to d. So, this right hand side, this approaches 2 times d square plus 2d square minus 4d square, which is equal to 0 as m and n both approaches infinity. So, this shows that norm of xm minus xn that approaches 0 as mn approaches infinity. Right? So, this implies that this xn is a Cauchy sequence. Now, since in H and since so in fact this is a Cauchy sequence in C, and C is a closed subset of complete space H. So C is also complete. So we'll get that which is a closed subset of complete space H, and hence is also complete.
Sir, did we have the completeness assumption in the theorem for H?
Yeah, I'm writing that H is a Hilbert space, right?
Uh,
So
but
in
all
fact,
Hilbert.
by this proof, you will see that if I assume this C to be complete subset of an inner product space, then also you will see that this holds, right? So, yeah. So what is your question?
Yeah. Here in the statement, we didn't say that H is complete.
No, by definition of Hilbert space, it is a complete inner product space, right?
Oh, okay. Yeah, sorry, I got confused with just inner product. Okay.
Yeah. So Hilbert space and Banach space, whenever we say, then completeness is already assumed.
Yes,
But
yes, yes. Yeah.
from the proof, you can see that I can write even weaker statement that if I have any inner product space and the C is a complete, just closed will not be enough, complete and convex subset, then also the proof will go through. Therefore, I am not writing H is complete. Here, what we actually are using that Xn is a Cauchy sequence in C, And if C is complete, then we will know that Xn will converge. So therefore, there exists X naught in C such that Xn converges to X naught. So if Xn converges to X naught, then we have norm of X naught is limit of norm Xn, because norm is a continuous function. So if Xn converges to X naught, norm Xn will converge to norm X naught, and limit of norm Xn, this is exactly equal to D. So this is equal to D. So we got a vector in C whose norm is the smallest. Right? Now we have to only get that there cannot be more than one such vectors. Thus, X naught is a vector of smallest norm in C. Now for uniqueness, suppose there are two such vectors. So suppose X naught belongs to C, Y naught belongs to C, such that norm X naught equal to norm Y naught equal to D. Then we want to get that X naught is equal to Y naught. So again, we'll just use the parallelogram law. So then again X naught plus Y naught by 2 by convexity, this is also in C, and therefore norm of X naught plus Y naught by 2, this is greater than equal to D, because D was the infimum. And by parallelogram law, norm of X naught plus Y naught by 2 square plus norm of X naught minus Y naught by 2 square, this is equal to norm of X naught square plus norm of Y naught square. And we have norm of X naught, norm of Y naught. These are both equal to D. So this will be equal to 2D square. This implies norm of X naught minus Y naught is by 2 square is equal to 2D square minus norm of X.
Won't there be a by 2 factor also? Because there's 1/4 and 1/4 which are coming from the first two parts.
No, no. Oh, yes, yes. So here also I need a half. So
Right. So we actually have 1/4 of X naught plus Y naught square plus X naught minus Y naught square. So that will be half of X naught square plus half Y naught square.
right. Yeah, that is correct. So this will be equal to half norm X naught square plus half norm Y naught square. And therefore this is equal to D square, not 2D square. So we get this is equal to d square minus x naught norm of x naught plus y naught by 2. Okay, so then we know that norm of x naught plus y naught by 2, this is bigger than equal to d, so this will be less than equal to d square minus d square, which is 0. And of course, this is greater than equal to 0, so this will imply norm of x naught minus y naught by 2 is equal to 0, which implies x naught equal to y naught. Right, so again you see that in this uniqueness, we are using the parallelogram law. So you may not expect that this will hold true for any non-linear space. But they are more general than Hilbert space where these results are true. This result is true. Right now we are not like discussing that. So, so this is an important result that if we have any like closed convex set, then we get this. And maybe let me write a corollary. Uh, so let C be a non-empty closed convex subset of a Hilbert space H then, and let's say we take any point. So yeah, so then for any x in H, there exists a unique vector. Let's denote it by PC of x belonging to C, such that norm of x minus PC of x, this is equal to infimum of norm of x minus y, where y in C. So that means this is nothing but distance of x to C. So here we are saying that if I have any vector x, and then if I look at the distance of x to this closed convex set C, then there is a unique vector which is for which this distance is equal to the distance of x to C. So how do we use the previous result to prove this? So
we can consider the set x minus c.
yeah, x minus c or x plus c, right? So uh, if we look at consider the subset x minus c. So since C is closed and convex, this will also be, let me write this as, maybe let me write instead of C K here, and then I'll use C for we are using Pk of x C is equal to x minus k. So this means that this is equal to x minus y such that y in k. So since k is a non-empty closed convex set, so is C. So C is also a closed convex non-empty subset of H. And then by the previous result, there exists a unique vector so let's call that vector this pk of x belonging to let's write first so there exists a unique vector in C such that the norm of that is the infimum. So that will be uh, let's call this x naught. So norm of x naught is equal to infimum of norm x uh, norm y y in C. But any thing in C, maybe let me not use y again. Let's use z. But any vector in C is of the form x minus y. So this will be equal to infimum of norm of x minus y, y belonging to K. And x naught belongs to C, so x naught is equal to x minus something. So which is x minus k. X naught is equal to x minus pk of x some pkx belonging to k. Right, so this is the vector which is in k, and because this x naught is unique, this pkx is unique. So basically pkx is nothing but x minus x naught we are taking. Therefore, norm of x minus pkx is equal to distance of x to k. And since x naught is unique, pkx is unique. Right. So what this is saying is that if you have any point and a closed convex set, then there exists a point in that set which is at the minimum distance, right? So, so these things, I mean, you can think geometrically that you have a point such that this thing, and I mean, geometrically, if you think, then when you have such thing, this vector x minus pkx, this is orthogonal to any vector in C, right? So, we will see that we can uh, get that if we have a subspace. So, so let me. Okay, let me first define these concepts of orthogonal complement, and then we will come to that. So first of all, we have already defined what we mean by orthogonal. So two vectors x and y in an inner product space are said to be orthogonal, and we write this as x is perpendicular to y if the inner product of x and y is equal to 0. This is the meaning of orthogonal vectors. And then if we have any set S, so for any non-empty subset S, let's call this inner product space V. V. The orthogonal complement of S is defined as, so the notation is S perp. This is equal to all the vectors which are orthogonal to every vector of S. So this consists of all x in V such that x is orthogonal to y for all y in S. So the vector which is the orthogonal to every vector of this set S belongs to the orthogonal complement. This is S perp. So, so clearly this S perp is non-empty. So 0 is always in S perp because the 0 vector is orthogonal to every vector. So that is true. And if we look at the whole inner product space V, then what is V perp? This has to be 0, right? Because if a vector is orthogonal to every vector of V, then it has to be only 0 vector, because if there is any non-zero vector, then x inner product with x has to be non-zero. So therefore a non-zero vector does not belong to V perp. So 0 belongs to S perp and V perp is equal to 0. And if we look at S intersection S perp, so a vector which is in S as well as S perp, then this has to be subset of the singleton 0, right? So any non-zero vector cannot belong to the intersection of S and S perp, because then again x dot x, the x inner product x will be equal to 0, and that will imply x is equal to 0. So this is also very obvious. It may be empty also, because if 0 does not belong to S, then S intersection S perp will be empty, and if S 0 belongs to S, then it will be equal to singleton 0. And if I have S1 subset of S2, then this implies S2 perp is a subset of S1 perp. So by taking the orthogonal complement, this becomes the other way. And another important thing is that this S perp is a closed subspace of P. So this again is easy, that if you have say x1 and x2 belonging to S perp, then any linear combination of x1 x2 that has to be also in S perp. That is by the linearity of the inner product, because if x1 and x2 are orthogonal to every vector of S, then alpha x1 plus beta x2 is also orthogonal to y for y in S. So this is a subspace, and closed is again because this if you have a sequence xn such that the inner product xn with y is equal to 0 for y in S, then by taking the limit we'll get that the inner product of x with y is also 0. So closed is also easy. So this is also easy, but let me write as exercise. And so this S perp is also a subset of V. So we can again take the orthogonal complement of this. So what happens if I take orthogonal complement twice? So if I take S perp, this is the orthogonal complement of S perp, and this contains S. Right? This is also very easy, that if you take any vector in S, then it is in the orthogonal complement of S perp. Again, they need not be equal. This can be strictly bigger than S. Okay, so this is done now. So now all let H be a Hilbert space.
So can we say that S per perp will be the smallest subspace containing S?
Yeah, you can.
For finite dimensional, it's true, but I'm not sure. Like, can we say this for infinite? That S per perp is smallest subspace containing S?
See, what you know is that this is a closed subspace which contains S, right? And if you have uh, see, if S is not a closed subspace, if suppose S is just a subspace, then also this S perp this will be closed. So
Oh, okay.
so you cannot say that it is the smallest subspace containing S. So maybe you can try to see whether it is the smallest closed subspace containing S, right? So because the definitely S closer is also a subset of S perp, right? So because of the closeness of this. So for finite dimensional, of course, the closure will be same as S. So that is there. So now let's suppose we are in a Hilbert space, and let M be a closed subspace of H. So then clearly we have, if we look at M intersection M perp, this will be zero vector, right? Because for any S, we know that the intersection can have at most zero vector, and if it is a subspace, then M and M per both contains zero vector. So the intersection is just zero vector. Now what we want is that can be write H as direct sum of M and M per. We will show that H is equal to M direct sum M per. So direct sum, the meaning is that uh, any vector H can be written in the sum of a vector in M and M per, and their intersection is zero. So that also implies that this decomposition is unique. So any vector in H can be uniquely written as a sum of a vector in M and a vector in M per. So first, let me just write this theorem. Let M be a closed subspace of a Hilbert space. H, and let X be a vector which is not in M. So we take a vector which is not in this subspace. So then there exists a unique vector y naught in M such that norm of x minus y naught, this is equal to distance of x to M. So this we have already done, because we have proved that for any non-empty closed convex subset, there exists a unique vector which is the distance is the distance of this to this. So this follows from the corollary. Okay, so I have to stop here. So next time I'll show that uh, this say now what we got, that if we have any x which is not in M, then I get x minus x naught norm is the uh, distance of x to M. Now we will prove that this x minus x naught will belong to M perp, and then that will imply that x can be written as the y naught plus x minus y naught. So x minus y naught is in M, and x minus y naught in M perp. So that way we can write any vector as sum of vector in M and M perp. So we will have to prove that this vector is in the orthogonal complement in M of M. And if x belongs to M, then in that case, of course, I can write x is equal to x plus 0. So again, that is obvious that we can write as a vector in M plus a vector in M per. So I'll do that tomorrow. I have to go for a meeting now, so I'll stop here.